Chika, can you hear me? Chika, can you hear me?
Yes, sir. Shweta is here.
No, Shikha, can you hear me? Shikha,
Yes, sir.
can you hear
Yes,
me?
sir. Now.
Okay.
Yes, sir. Yes, sir.
Today, the first, one of my oldest students now is working in a TCS, the senior member in TCS. I think more than 10 years working in a TCS. So he's supposed to give the demonstrations of proteus software, whatever you required, right?
Yes.
So whatever you have
Okay,
the
sir.
questions, you can ask him. No issues. He will be explaining. He will be joined shortly because maybe his computer is, they don't want to use the app. That's the biggest problem because TCS there is certain restriction is there for his computer. So he will be joined within a 5 minutes.
Okay, sir. Okay, sir.
Now it's possible for you.
Yeah, it's possible.
Student, are you downloading the 8.1?
No, sir. 8.6.
8.6? Or more or less same. There is no problem at all.
Okay, sir. Can I start?
Yeah, you can start, Rajeshi. You just give me an example like LCD interfacing.
Okay, sure.
The circuit, the programming. Just make it how to design and how to it will be done. Okay. And if you have
Okay.
already designed something, you can show to that and how to how to design and how to run the program and where the write the program. You should explain all those things.
Okay.
First
So,
of all, I am introduced Rajeshi. Rajeshi is one of my best students, and he is working in the last few years in TCS, and he also is my oldest one of my oldest students, and he's a bright student. You can say, and now he's well established. I can say, and he is working in TCS. Rather than the TCS, the hardware interfacing and everything. Whatever you are doing the project, Rajeshi know all those things. And in the time of Rajeshi is doing the proteus, and he is doing well in the proteus. So Rajeshi, now you can start.
thank you, sir. So, I will start in a bit, modular basis. First, I would like to show the students how to make a new project in Proteus, because nowadays, starting from Proteus Suite 8.1 and onwards, we are able to make a new project as well as create ASM files and assemble and run them intrinsically within the Proteus system. We don't need to use any external assemblers or hex file creators, etc. So let's start with a simple microcontroller project. Just an LED will blink. That would be the basic one. Then I will, as you said, then I will try to uh, fully design an LCD circuit and will show how it works. Okay, sir? Every time I would recommend using this project wizard when you start using Proteus, because this gives you the freedom to choose your firmware as well as choose your workspace and everything. You can do a design by directly clicking the ISIS icon here, but it's not actually recommended. We do it in this way. Let's name it project 1, and we would make it in desktop. We can choose or it will be a basic project like using controller ICs, 5 or pre-hardwired ICs, or maybe registers, capacitors. Choose if there is no microcontroller firmware project, and if there is choose the family. Guys, am I audible?
Yes, sir.
Okay, thank you.
Absolutely audible. Absolutely.
Thank you, sir. So we are creating here a project on 8051 microcontroller. So we are choosing the family as 8051, and we all know that the CMOS version is 80351, sorry, 80331. So we are choosing the controller as 80331, and there is a compiler that I have installed previously in the system. There's a SM51 compiler. This we will use to compile the assembly language program we have written in the prompt. So that's it, guys. Let's start. So these are the things we are going. The schematic template is an A4 sheet, because if you print it out, it will be better in an A4 format. And the farmer is 80331. So we have this screen. You can see here, they have already placed the microcontroller so that we can design it very easily. And just 80C31, and we could have used 80C51, 889C51, whatever we have the microcontroller in our hand. We can use any one of them. So here is the microcontroller, and they actually make the schematic in this way that the basic components, all the basic components are actually inbuilt, and you may or may not connect them, right? Like if you don't connect the crystals here, then also this simulation will work, because Proteus will, take it for granted that the microcontroller is connected with its basic components like the reset or the crystals or the capacitors, etc. But anyway, for the sake of designing, I will add all the components one by one, and we'll try to make a basic circuit, a very basic circuit with a very basic code. So let's start with the crystal. We have to press, we have to understand few hotkeys from the keyboard to make this designing process a bit faster. We can start with placing the components. If you press P from the keyboard, I am pressing P for Papa. I am pressing P from the keyboard to get the list of the components. P stands for peak here. You can write down the name of any component, and you can see the simulation model of that component in the big window. Like in the keyword, I can write the name of capacitor. Whenever you give this keyword, you'll get this thing. See, there is a list of capacitors here. We will use ceramic disc capacitor because these are the small and non-polar capacitors we use along with the crystal. So there is ceramic disc, and we'll use 33 picofarad capacitors. So let's search from here. Here we have 33p. we will put it. Again, we have pressed P again, and now we will search for the crystal. We have a quartz crystal here. We can set the frequency in the circuit itself. So this is the crystal and this is the interface, and we'll place it. We will also place some registers we will require for the reset. We need a 4K7 register. We will use 0.6 watt metal film resistors here. So this is M4K7. We'll just double click it. When you have to add multiple components, you can double click on any of the components and it will get linked in the pane you have in your main screen, and this peak devices screen will not close. We have added this one. We can also add a button switch that we need for the reset. In the switches and relay subcategory, we have switches and buttons. We may need an LED. In the optoelectronics section, we can find these LEDs, and there are some animated LEDs here. All the components that are from this active library, there are some libraries. You can have the active library in your system. These active components are animated. You can see the animation in the component when you are simulating the project. So I am taking a blue active LED, and along with the LED, I can take some register. That will be 220 ohm register. For ohm, we write here R. R is the symbol here for ohm. Okay, so these are the components right now we will need. Again, if we require anything else, we will again come to this screen. So let's start with the reset circuit. They have this reset technology here already embedded. I will delete this. And what I will do, this is also terminal is not required right now. And for reset, we also need a capacitor for power on reset. So we will need a 10 US capacitor, and that will be electrolytic. It's not there. Okay, we have a 10 US capacitor here. That is electrolytic. We will add this. Okay. So clicking the plus button in your keyboard, that changes the orientation of the device. So if you want a good design, you have to be cautious about the orientation of the devices, because otherwise your design will be a mess. So in this orientation, I have put it, and also I will put a button in parallel to that. The button is already in a perfect orientation, so I'm not moving it again. We will do this in this way, and then connect it to the reset. We will also sort it so that the capacitor and the button are parallel. And there are something, those are called intrinsic things. We can put a power rail anywhere, and Proteus itself, through its artificial intelligence, Proteus knows that the power will be 5 volt or 12 volt wherever required. So you can put a power rail anywhere, no need to mention the voltage for that. But again, it's a best practice to use a voltage terminal. I will show you how to use that. But for the ease of designing and quick accessibility, you can use the power rail. Just right click, place, terminal, power or ground, whatever. You have these things here. So you can put power or ground, anything. And you see, this is a sticky component and it has got stuck with my mouse pointer. I can press the escape button from my keyboard to get rid of it. just like this power rail has got stuck with my mouse. I'm clicking escape, so it has removed. Okay, so now we will put a register, that is the 4K7. We also can use 8K2 registers here. I think that isn't better recommended, but anyway, I can use it. And again, there will be a terminal component that is the ground. For all the circuits, we need a ground. We put it here, and so my reset circuit is done. Now we will be connecting the crystal. To choose the components from the left pane, we click on this components mode, this one. Okay, so we have here crystal, selected it, and we will put it somewhere just here. We can select a whole component like this, click on it, and drag it over the screen to make some space for any component that is in between. So this is the crystal. We put it here, or rather here. We connect it to the crystal pins. We'll put some capacitors. Those are 33 picofarad. Sorry. If you have clicked any, I mean, there will be a new wire starting to be. So if by mistake you click on any of the wire, it just hit escape from your keyboard so that the sticky wire goes off. Anyway, so we have a capacitor here. We are putting it in this way, or maybe in this way. We will put it here for better visibility, and we will connect them in this way, and again connect them to the ground. So this is basically the crystal circuit you see here. These two are the crystal pins. We have put the crystal in between these two pins. That means 18 and 19. And from each terminal of the crystal, we have put a 33 picofarad capacitor from terminal 2 and terminal 1. Both the terminals of the crystal, we have put a 33 picofarad capacitor, and we sorted the opposite ends of those capacitors and put it to the ground. This is basically the crystal circuit that we use for any microcontroller or microprocessor. This is the damping for that crystal oscillator. So far so good. For my first program, I would try to blink an LED from this device. So I will put an LED here. To select the LED, I will move it in this way and say connect it to port 1.0. It's done, and we'll put inrush register to it so that it doesn't burn out. So we have here a circuit, a forward bias LED we have here, limiting resistor to limit the current. There is a 220 ohm resistor we have put, and this is grounded. So if we make the port 1.0 high, that will glow the LED, and if we make it low or reset it, then it will dim the LED. So that will be the circuit. So I think I have a program already written for that. Let me check. Otherwise, I will write it again for you. I'm checking the program. Okay, sir.
Okay.
I have it here. This is a very simple program. I mean, old school class 1 program. This is. And I have it. So whenever you create a project, you get it here. The source code is already structured in this way. The Proteus makes it automatic, and the structure is maintained. So you have to write your code here. I will talk about the rest of the components of this script in detail in upcoming sessions. And for now, let's write down the code here. So what we have here in my code, I wrote it to start from 0000 hex, but right now at this scenario, it's not required. I will say you why it's not required. I'll let you know. I'm just deleting it. I have a loop starting here, it's back. We are setting port 1.0. That means the pin 1.0 will be high. Then we will call a delay. The delay subroutine is written here. And I guess I don't need to talk about this thing in more detail because we all know what delay subroutine do. And after the delay is done, we will clear the port 1.0 pin again and then again call delay and then look back to the previous part of the program. And also there are two end statements, those are not required, so I'm removing my end. And now why I have removed the org 0000 hex from here? See, in this program, as this is done by the Proteus simulator itself, we have a reset vector table here. Proteus intrinsically sets this reset vector table as starting from 0000 hex, and then it calls the start segment of the program. That start segment it originates from 0100 hex. So everything we write as a program in Proteus that is recommended to be started from 0100 hex. So for 0100 hex, we have all our code segment, and that code segment is called right after org 0000 hex. So whenever you click the reset button of your microcontroller, it immediately calls to 0000 hex, and whenever the 0000 hex is read, I mean the next line of 0000 hex is read, there is a statement to jump to the 0100 segment, that is your code segment. So eventually your code gets reset. This is why we are removing the 0000 hex from our program. That is also not a fault. We can start our program from 0000 hex, but whenever you are trying to write a multi-branch program and you have to maintain a vector table for that, we will keep the 0000 hex and subsequent few addresses, few positions of the memory to write down the interrupt tables, vector tables, etc. There will be reset vectors and also other interrupt vectors are there. So you can write down all the vector identifiers in that 0000 hex location, and then you will start writing your program right from 0100 hex. So that's why we are writing this code in 0100 hex. So that's it. I don't think there is anything for debugging here. We'll just save this code. Okay, and fingers crossed, we will try to simulate this code here. It's already linked, the code is already linked. So whenever we will click the play button, this is the play button that we use for simulation. Whenever we click the play button, the simulation should start. Let's give it a try. Okay, I guess something is missing here, and yeah, the simulation has been started. It took a little bit of time to see all the branches of the code and everything, and see the LED blinking we can see here. So this is related to the delay subroutine we have written. So if we pause the execution and see the debugging screen, we can see the delay subroutine was being called right here we have the delay subroutine, and this is the position where the execution is currently paused. So if we play the execution again, LED blinks and again delay is called, LED turns off and again delay is called. So most of the times the execution will be here because the delay subroutine will be governing the timing of this circuit. So that's why we are having this selection here. So that's it for now, and now we will try to design some LCD interface for this thing. I had some LCD interfacing designed here, but it may take some time to find it out. Design it, some ports and everything. Select the whole. Sir, one thing, should I let them? I mean, should I show them the oscilloscope and virtual instruments before going into our interface?
Yes. You can.
So, thank you, sir. Other yes, that we can use to debug and also go. Because for microcontroller, we have a programmer, we have debuggers and all, and most of the times the results are predictable. You can predict that, okay, this program will output these type of things and this program will work in this way, whatever. But for the basic electronic components, like for the capacitor, for registers, etc., also maybe for the 555 IC or any other ICs, those are analog in nature. So for those ICs, sometimes you can see there are much difference between theoretical and realistic approaches. I mean, theoretically you design something, you thought about designing something, you see this component will work in this way or that, whatever, and you have made a circuit based on your virtual thinking, and whenever you try to implement that thing in real life, there are some problems, random problems start occurring, like sometimes the capacitors that don't get charged in the way you have designed because they are leaky. Sometimes the registers get heated up and you are not able to maintain your inrush current, or whenever they blows up due to overheating. So these real life scenarios, Proteus is a very good area. You can simulate your circuit first, and if Proteus gives it an okay sign, then you can definitely make it in real life. So for that judgment and for that real life simulation, we also have some components here, also some laboratory components that we usually are able to see in our basic electrical laboratories or basic electronic laboratories. Those components are also present in Proteus. Those are called virtual instruments. We can put this type of virtual instruments here: oscilloscope, we can put analyzers, counters, and voltmeters, ammeters, and wattmeters. So this is the best thing, one of the best things we have in Proteus. Let's, for example, we put an oscilloscope here, and we will connect one of the, it's a 4-probe oscilloscope. You can connect 4 probes in 4 different signal areas. Let's connect one of the probes in the output pin we are programming. We have programmed in this microcontroller, and let's see what the output of the oscilloscope becomes. Let's resimulate the program. We have the oscilloscope here, and you see it. This is the A. This is the pin for the A, and we have connected an LED. You just look at the LEDs blinking, and you can see the peaks and the troughs of the oscilloscope reading. This is the A signal, the signal corresponding to channel A of this oscilloscope. Whenever the LED glows, you can see here the signal is up. And also there is some minimum gradual fall you can see here. This minimum gradual fall is something that is the overall parasitic capacitance of this circuit is doing, that you cannot predict in your theoretic theoretical circuit. In a theoretical circuit, we do not consider this type of parasitic capacitance, but in real life, this capacitance happens and this thing stays there. And none of our circuits are till now capable of maintaining a strict and flat curve in this way, because every time we connect it to a power source or wherever, there are some parasitic leakages, capacitive leakages, and also we have some components of frequency of the radio devices we have in circumference. All those radio devices, sometimes they contribute to the output of any signal. So there are always some this type of frequencies here and this type of leakages here. So those one of those leakages you can see here in the oscilloscope you are seeing. We can also make some changes in this code to see the oscilloscope in, say here. We can set another pin. Let's set P1.1 and then again call delay. And then clear the same thing. Then again call delay. So what it will do now, it will first set the pin port 1.0, then reset it, then again it will set port 1.1, then again reset it, and this cycle will continue. We have made the changes. It has been compiled automatically. Whenever you save the program, it's already compiled. Now let's do one thing. Let's connect the port 1.1 pin, I mean the second pin of port 1 to the second channel of the oscilloscope, that means channel B of the oscilloscope, and see what are the signals that are presented here. Okay, so what it will do, it will light up the LED in a particular cycle, and then the LED, the LED will be turned on, and whenever the LED is off, then we will get the port 1.1 pin as on. You see the fluctuation here. This is the time the LED is on. This is the time the LED is off. That is connected to 1.0. And for 1.1, this is the time port 1.1 is off, and this is the time port 1.1 is on. So this is the manifestation of the second pin. I mean the new pin we have connected here. It will be turned on just after this one is off. Also, we could have done another thing, just to make it a bit legible. We turn it on, we call a delay, we clear it, and then we don't call this delay. We just remove this delay so that as soon as port 1 is turned off, then port 1.1, I mean as soon as pin 1 is turned off, then this pin will be turned on, because we are not calling a delay here. And again, as soon as this pin is turned off, we are removing this delay, and this will be set. So port 1 will be set, I mean pin 1.1, 1.0 will be set. It will be a delay then it will be reset, and at the same time 1.1 will be set, there will be a delay, and when it resets at the same time 1.0 will again be set. So let's see what happens here. See here, that is a better for understanding. Whenever this one is on, this one is off, and whenever this one is off, this one is on. That is because those two are alternating the turn on signals here, 1.1 and 1.0. Whenever 1.0 is on, 1.1 is off. So we can see the manifestation is better legible in this format. You can connect, if you don't want to put unnecessary LEDs and anything, you can just connect an oscilloscope and see the output of any signal. So for now, we can start designing something with an I have forgot to put some voltmeter here. Let's also show that. We have a DC voltmeter. So let's do one thing. We'll put the voltmeter here and then ground it. We all put voltmeter in parallel, so that's why it's parallel. It is starting the simulation. See, we just have an alternation of voltage 4.77 volts and 0.02 volts. That means voltage tending to 5 volts and tending to 0 volts for this pin. For this pin 1.0, whenever the pin 1.0 is on, we are getting here. See, this is on and we have 4.77. This is off, we have 0.02. 0.02 that tends to 0, and the 4.77 that tends to 5. So that's all we have here. This is the voltmeter. Also, we can measure flow of current from this IC. Just for example, I am showing you this. We usually do not measure flow of current in this scenario because we all know that there is a 5 volt and there is a 220 ohm resistor, and the internal resistance of the LED will be approximately 30 ohms. So that makes it 250 ohms. So what's the amount of current will flow through here? We all know. But anyway, for example, I can put a virtual instrument and a DC ammeter I need to put here. And we all know that we put ammeter in series so that all the current that flows through the circuit also flows through the ammeter and then gets drained. And we have put the polarity wrong. Have to remove it. So this is the correct polarity. I mean, current goes through this way and then gets ground. The simulation, you see very little amount of 0.01 amps of current flows when the LED is on, and when it's off, then 0.00 amps. That's pretty cool because for 5 volt input and a resistance of approximately 250 ohms, the amperage is very small, and that's why due to the the limitation of the instrument, it's just showing 0.01. Means there is a little amperage there. I mean, negligible current is getting flowed, and when it's off, then no current is getting flowed. So these are the virtual instruments we have covered. We have covered the oscilloscope, the ammeter and the voltmeter. We have talked about the ground and the power, and regarding some specified input. We can place components we have already picked from the list. We can some generator. We can place DC generator, we can place sine wave, pulse, exponential, and many type of generators are there. We can place for this. I mean, say you have to design a circuit that uses some pulse wave or some sine wave for as a trigger, and then it works in its own fashion. So for that circuit, you will have to design a pulse wave generator or a sawtooth or a sine wave generator in your real life, or else you have to use a function generator device that is available, and a very overpriced device is that. And for the simulation of that circuit, you are not required. You maybe the thing is like this. You don't know what is exactly inside a sine wave generator or whatever, but you have to place a sine wave generator in your circuit, for example. So in those cases, you can just use a generator component from here. This will generate the sine wave for you. So just put it here, double click on it. You have the peak voltage, I mean the highest amplitude of that sine wave. You can select sine wave from here. This is the offset that usually we put as 0, and this is the amplitude here. This is the timing, I mean the frequency you need to propagate for that sine wave, and the delay. So I will just connect this source to, and you will get a DC connection. I mean DC 5-volt connection. So what I will do, I will just and you will see
सर किसी की आवाज नहीं आ रही।
हाँ, नहीं आ रहा है। वो शायद उसका नेटवर्क का प्रॉब्लम है, वो निकल गया है और फिर घुसेगा शायद।
ओके सर।
Okay, so we have here the simulation was already running, but anyway, connectivity got lost. So we were doing this thing. We were just animating this switch to see this reset happens here. Let's press it. As soon as we press the switch, you see the reset is gone red. I mean the gray square that's just beside the reset button that goes red. So any such buttons here in your component, I mean beside your component, whenever they're blue, you see this thing is off, and whenever they're red, you see this thing is on, and whenever they're gray, we call it tri-state because this is not actually either on or off, because whenever you put a circuit in a circuit which is based on microprocessor or microcontroller in a bias position, and if you don't configure any button, they are actually put in this state. This is the gray state and tri-state, and you can configure any state for this particular pin in your program, and as long as you are not configuring that pin, that is put in this way. So that's it. These are the output pins, and that's why they are always red. That is previously configured in such things. If you don't, for any microcontroller, if you don't configure any output or input pin, I mean any IO pins, if you don't configure them, they are usually put it in this way, except port 0. For port 0, they will be in tri-state if you don't configure. That is a theoretical details. I just can't remember what are the logic behind that, but as far as I can remember, these 3 ports, they will be configured as output, and this port will be configured as input unless you configure any of these ports in your program. So I have just configured 2 pins. I haven't configured this port. So this port is by default configured as an output port and put high, but these 2 pins are working in a program that I have designed, in the way the program I have designed. So that's it. Let's go for a bit organized project. I will just remove all this stuff from here, keeping this microcontroller, obviously. I will need this microcontroller again. So I will remove this, I will remove that also. Sorry. And also this one. So this is the basic components. These are the basic components for the circuit. Okay. To move any part of the circuit, I mean in the screen for sake of visibility, just like we cannot see the bottom part of this microcontroller, you just middle click your mouse. Do you know how to middle click, students? You just put your finger on the scroll bar of your mouse and click on it. You will get this icon, and by middle clicking it, you just drag your mouse in the screen. It will show as a whole. You can put it anywhere in the screen, just middle click and drag, and whenever it's finished, you just click escape. So I will put it in this way here, and I will try to put some LCD. Let's see if I have already some designed LCDs in my project. So give me a moment, guys, okay? I will just import this thing. This is an LCD that I have imported from another project that I had earlier. That is LM016L. That is a 16 character LCD. But in your project, you will use a different LCD. But anyway, if you use the LM018L in your project, that will resemble the same. That has the same pins your LCD has. Your LCD has the RSRW and enable pin. These are the 8-bit data bus that your LCD will have, and it will also have VSS, VDD, and VE, so that you can adjust the contrast and everything for this. So for RSRWEN, we connect them in our usually in our genre of circuits, we connect them to port 1, and for the data we connect them to port 2, if I am not wrong. I will consult the port project. We connect port 2 to the data and port 1, yeah. Port 1 0 will be connected to RS. Port 1 0 will be RS, port 1 1 will be RW, and port 1 2 will be N. Okay, so port 1 1 we have here. Port 1 0 will be RS. We are connecting just in this way. You just click on it to get the box, just drag the connection and put it in this way. Hello. Hello, sir. I can't hear you. Hello. Sir, are you trying to say something?
Yeah.
Sir, are you trying to say something? I couldn't hear.
No. You continue.
Okay. Thank you, sir. So we have just connected these 3 pins, port 1.0, 1.1, and 1.2, to the 3 pins of the RS, RW, and EN, and we will connect port 2 with the data one. So you guys, I guess you have already, got your circuit for your project. I mean, so if you have the project circuit in your hand, you will see that usually LCDs, they design the LCDs and connect them in this way. This will be a bit complicated here. Later on, I will show you how to make a neat connection for this. For that, you will need some more space also. Let's just focus here. We will make some space in this way. We'll draw it, and then we will remove this wire and connect it again. So 0 to 0. Best option is to do it in this way. 1 1 2 3 So this is something we do in the data bus. We have we have connected each of the pins to one of the data pins here, and we have to maintain the chronology. The 0th data pin is connected to the 0th data pin here, and the 8th data pin, that is for 2.7, that is connected to the 8th data pin here, and all the pins in between, those are connected in the same fashion. I mean, the first output of this is the first input of that. This is the thing we have here, the LED that is for just to make sure that this circuit is getting power. We are putting this LED in your LCD screen. I mean, the LCD displays you will use in your project. You will have a backlight LED for that LCD. I wish I could have shown you here. I had one of them with me. I bought earlier. But anyway, if you see the LCD screen, I mean the LCD component in your project, in the bunch of your project components, if you take the LCD out, you will see that there are two dedicated pins for the LED. That means the backlight of that LCD. So right now here the LCD I have that doesn't have the backlight, so I have put the LED here just for demonstration. Okay. So this is the resistor, the 10K resistor we put here for contrast adjustment. Right now, this will be of no use because this doesn't have the background LED, so we will not be able to increase or decrease the contrast. And here in the microcontroller itself, we have to modify the source code. I mean, we have put an LCD screen here, and there are some other components and everything. So we have to modify the source code to see if this LCD works or not. So for that, I think I have a circuit for some LCD designing. Give me a moment. I will search for that circuit. Let's see. let's see if it works what I found here. I had this program, but I'm not sure it has been debugged or not. I just got it from some scratch. Should work. The messages are 1, 11, 2, 21, 31, and here I have 1, 11, 2, 21, 3, and 31. Message 3 is missing from here. Oh yeah, message 3 is there, and 31. Okay, fine, so it should work. And there is this one, fine. Okay, let's see. It's compiled. Let us check. I'm telling you again, guys, I'm not sure whether this program is gonna work or not, because at this short point of time, I'm not able to debug it. Let's fingers crossed.
Okay, I will be seen. No issues. I am there.
Okay, I have a problem here. Jump conf this is not there. Thank you, sir. Conf this, that is the configuration display part, and I guess, yeah, that's here. One thing. Maybe it's this time. Maybe.
Rajoshi, S jump is not working over here.
I guess it's not working. I will see.
So you should be given A jump. S jump or A jump. There is a no only jump is not there.
Yeah, A jump. I forgot actually. Thank you, sir.
And go upward. Another
Okay.
S jump is there. Another 1, 2 S jump is there. Go downward. Go downward. Go downward. Go downward. Go downward. Yes.
This will be a jump. Fine. There are some more errors I can see, but they're not mentioned. Let's see. Let's stop the simulation.
Which line error is detected?
No. Let's see. Yeah. Will not defined here. Okay, so these message symbols are not defined because after it, no, the statement is fine. Let's do one thing. Let's do a trick. I think I also have a hex file that is previously compiled for this circuit. I will just try to find if I see that hex somewhere. Give me a moment again, please.
Again, how many error is showing?
11 errors are there, sir.
Till now?
Yes. Yeah. This message bytes, they are actually not getting read. I'll search for some debugging. These are fine. I guess the error is with this DB thing. This is
DB is
symbol
not
not.
taking.
I think so, because that is
After
red.
DB, you just given a colon. But colon is not required actually.
Colon is not required. The colon we didn't put colon in our project. This new compiler is something that is causing the problem, because the same code works in the ASN31, but unfortunately the ASN31 itself doesn't work here. I can do one thing. I think I have the hex file already compiled somewhere in my computer. I will search for the specific hex file. Okay, I got one hex, that is lcd.hex, but I don't know what's inside that. I'll do a random thing. I will just change this. See, if you students, if you are in such a jeopardizing situation, you cannot change the source and you don't know how the where the source is getting glitched in the compiler. You can do one thing. If you are confident with the source code, if you know that your source code is good, and maybe something in this particular compiler is causing you a problem, then you can do one thing. You can externally compile that source. I mean, if you have an assembler like ASM31 and a converter file like bin2hex.exe in your system, you can write down and convert that code to hex and then directly feed that hex. I mean, override everything from here and feed the hex directly from here. See, in my desktop, I found this thing. These hex files I have already found. So I will just, I guess, see, this is a file I have created in 2013. So it's obvious that I don't remember whether this lcd.hex worked or not. But again, I will give it a try. I don't know whether this file, what are the exact informations that this file have, did have at that time. But anyway, I will give it a try for demonstrational purpose. I will just change it to that file. Okay, so see here, it has been changed from the temporary debug file that was created by default by the Proteus. It has been changed to lcd.hex that I have provided. Okay, so let's start. Oh, I have to unlink this one as well. So what I will do, I will remove this file and I'll change this to this. Is done. Let's see if it works. Okay, so voila, it works. So the hex file that I have fed to it, that was something I made for the students of BIT, sir. 2013 BIT batch.
Yes.
Okay, so these guys, they are your senior. They are from the same university you belong to. And I have made this for those guys. And luckily, just by luck, that code worked. And you see, we are getting some display in the LCD as well. So unfortunately, I couldn't show you the program because that program is no more.
Program will be also working. I don't know. JMP is, you are written the last loop. JMP.
Yes.
Why is JMP is mentioning? I don't know. JMP is no instruction is there.
Yeah, there is A jump or S jump. I can remember. JMP
A jump,
is not.
S jump, L jump. There are three
Yeah,
types of
L
jump.
jump. Yeah, three type of jump. Absolute, short, and long jump. And anyway, sir, I will check for that thing, and I guess I will get another session for this guys to interact with. Can I have another session in 1 week or two, sir?
Possibly maybe in a Sunday, so there will not be any problem.
That will be best for me, in fact, because
Okay.
today I am already getting calls from my office, and I just told them that I have network problems.
Okay.
I'm doing this anyway. I will definitely conduct. I'm glad to conduct some more sessions on this. And regarding today's thing, let's start it again. It always gives you a pleasure to see the LCDs and everything working, even in simulation and also in the real life.
Yes.
And so it actually works. You can reset the circuit. But I don't know why the reset is not working. Maybe, yeah, the reset is not working because the wordy thing was there in 0000, and this thing is meant for 0100. Maybe that's why the research isn't working. I will check it again. Anyway, so the rest of the things are working. And so today, what are the takeaway points from this meeting? For the students, let me uh, recollect once again. So we have learned how to put components in a circuit. What are the components that we can animate in a circuit? I mean, see this LCD screen is also an animated circuit. I mean, the animated component, one of the animated components. The LED, that is an animated component. This switch, this one is an animated component. So we know which are animated components and which are non-animated but functional components. We understood how to rotate or place a particular component in such a manner that doesn't affect the components those are beside that. And also we have understood that intrinsically Proteus takes some of the components as its base. I mean, some of the components as the base components of the circuit, and it also assumes that those components are connected with the minimum bare requirements. I mean, for a controller, Proteus always assumes that whenever you are putting a microcontroller, you are connecting it with a crystal and the corresponding capacitors, the reset circuit, etc. So you don't need to configure them in a different way. I mean, you don't need to configure them manually. If you always can configure if you want to, but it's not that way required. And also it provides power to all the components those are active. I mean, an LED is a passive component. You can put an LED without biasing it, it will not glow. But if you put a microcontroller in a circuit, you see the power pins of this microcontroller are not present. If you zoom to this microcontroller, you will see that all the pins are there except the power pin. The power pins are absent. The power pins are actually taken for granted by the simulator itself. Proteus is a simulator. The simulator itself considers that the power pins are there and also considers that they are connected to the power rail. So you don't need to connect the power pins exclusively for any microcontroller. And also, if you don't connect this LED power, LCD screen power, it will also work. I have seen it work. Because for all these active components, they think that these are already supplied with power. So that's the second and third thing we have to discuss. We have learned how to give a source input. I mean, you can give a source DC or a source sine wave, whatever you like. Also, we have learned to use the virtual instrument. The virtual instrument is a very important thing for debugging a circuit, especially if you use basic electronic components like resistor, capacitors, and diodes in your circuit. The virtual instruments are a very good tools. The virtual instruments are very good instruments. You can place them and you can also read out the nodes of the circuit, what the circuit tells. So these are the virtual instruments. We have used few of them, not all of them I have covered. I will cover if I get time. This is the basic components I have covered. We have learned to insert terminals. Terminals means the power and ground. Those are the mostly used terminals, but also we can use input and output terminals that you can connect with your serial port in the computer you are using. And you can also check the manifest in your external hardware. That's it for today, I guess. And now I will be online for again 1 or 2 minutes. You can ask any question if you have to demonstrate. If you want to know about anything that I have demonstrated today, you can call me. You can tell me in this session. So, any questions from anyone?
नो सर हम लोग पहले ट्राई
Sir, I want to ask, sir, how we can simulate? What is the process of simulation?
That is what I have shown you. You just create the circuit, everything is done. Then there is a play button here. Do you see the play button here?
Where, sir?
As soon as you click on this play button, it goes green and the simulation starts.
Okay.
Okay, so for any circuit, not only for the microcontroller or anything, for any circuit, the next day I will show you an activable multivibrator circuit with a 555. There will be no microcontroller, no LCD, nothing. There will be only a 555 IC and some external components, and you will see some LED glowing or something like that. I will show you next day. You will see for every simulation, you can just click on this play button, it will start, and the simulation will be on your screen. Okay, next.
Okay, sir. Sir, can we use any Proteus version or the same that you are using?
No, I would recommend you go through. There are as of now there are 5 versions of Proteus. Those are available in the sites we use to download free software. Proteus is not a free software, mind it. Proteus is an industry software and it's very much costly. We are using cracked versions just for educational purpose and non-commercial usage. So you get Proteus 7, Proteus 8, and there are several sub-versions of 7 and 8. 7.4 is there, 7.9 is there, 8.1, 8.6, and 8.4 are there. So you can use any one of these, but I would recommend using any version which is beyond 8 or 8.1. I mean, any versions which are newer than 8 or 8.1 you can use. And also one thing to keep in mind, whenever you are installing Proteus, first before installation you import the license file, right? There is a license file import wizard. We click on it, we import all the licenses, and then we install Proteus. So while are you importing that license file, make sure the active component library is there. Because if the active component library is missing, you won't be able to see the manifestation of these active components. I mean, your circuit simulation will work, but the output will not be like this in GUI. You will get some MATLAB-like output that the components are working, but they are not active. You will not see the glowing of the LED or the display in the LCD or anything. You will just have to debug every node of your circuit with some analog or digital debugger, and you will see the outputs in that debugger. You will not get any active components. So make sure that the active library is there. The active library is there. You will see all these the GUI thing.
Okay.
Thank you.
রাজশ্রী, আমি না তোমাকে একটা গ্রুপে অ্যাড করে নিচ্ছি। তুমি ওই 8.1 যেটা বললে সেটা কিভাবে ইনস্টল করতে হবে সেইটা তুমি যদি একটু ওদের বলে দাও তাহলে ওরা সুবিধা হয়। ঠিক আছে?
হ্যাঁ স্যার, আমি একটা ভিডিও পাঠিয়ে দিলে মনে বেটার হবে। আপনি আমাকে গ্রুপে অ্যাড করে দিন, একটা ভিডিও করা আছে, আমি ভিডিওটা দিয়ে দিচ্ছি।
হ্যাঁ, আমি তাহলে তোমাকে ওই গ্রুপটাতে অ্যাড করে দিচ্ছি, তাহলে সুবিধা হবে। ওকে, ওদের যদি এরপরে ওখান থেকে কোন তোমাদের রিলেটেড কোনো কোশ্চেনস থাকে ওরা করতে পারবে, সফটওয়্যার রিলেটেড ইনস্টল বা কিছু যদি হয়।
ওকে স্যার, ওকে,
ঠিক আছে, তোমাকে দেখো আমি গ্রুপে অ্যাড করে দিয়েছি।
ওকে স্যার।
হ্যাঁ, প্রজেক্ট গ্রুপ। থ্যাংক ইউ। ঠিক আছে, আমি এখানে I will put a video here. I will put a MP4 video here, and that is self-explanatory. You will get how to install Proteus, what is the pre-installation things, and what are the post-installation things you have to perform. Once the installation is finished, you will be able to use the Proteus 8.1. You can also use 8.4, whatever.
Yes, sir. Actually, we are facing problem in the. Okay.
In 8.4. Hello.
They are maybe 8.6, I think. In the morning, you are saying.
Yes.
Okay, no.
Yes,
issue.
sir. I have 8.6.
No issue. You can use it. I will just try to install 8.6 in my system, and we'll see if anything is different there. And if I find anything, I will share to you. And also, I will share the link for downloading 8.4 or 8.1
8.1, I think it is best because you are working in 8.1, so 8.1 there is no problem at all.
Okay, so I will share the link for 8.1.
Okay, they will be installed 8.1, no issue.
Okay.
Oh,
8.1, 8.6, no problem at all. Something it should be done. That's is required.
yes. Okay. Okay. So for today, can we put this session to an end?
So your time is now wasted.
Yes, sir.
No.
Rajesh, you go, you do your office job, and we are again meet on Sunday. I will be send you the link. Okay.
Okay.
Before that, you everyone should be have installed your software and do it properly. If any queries if you have, you can ask in that particular things, right? Hello everyone.
Yes,
Yes, sir.
yes, sir.
Yeah.
Yes, sir.
So Rajashri, end for today.
Okay, sir. Okay. Thank you so much, and thanks to me for attending this
Rajashri,
session.
you are now
Thank
host. So
you. Thank you, sir.
you should be in the meeting.
Okay. I'm ending the meeting. Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay. Bye bye.